All right, let's go ahead and get started. I want to welcome you to this second screencast for acids and bases. This is Unit 12. And we were looking at this relationship, the relationship between pH and the hydrogen ion concentration. And we said that the relationship was that the pH was equal to minus the logarithm of the hydrogen ion concentration. So first of all, what do we mean by logarithm, this log symbol? What does that mean? Well, it's simple. It means power as long as you're talking about base 10. Now, if you're talking about base C, and your math teacher will talk to you about that a little bit later if they haven't already, the natural log is going to be to the base E. But here we're going to restrict our discussion to base 10. In fact, we can even write a little 10 right there, some people do, to indicate that the logarithm, the log that we're dealing with, is to the base 10. So, what does logarithm mean? It means power. That's it. As long as the power is 10, as long as the base is 10, we just look to the power, and that tells us what the pH is. So let's take a look at some easy examples, ones that we don't even have to use a calculator for. So the hydrogen ion concentration, let's just say we've got a hydrogen ion concentration of 1 times 10 to the negative 2. And somebody asks you, what's the pH? Well, just look to the power, right? The formula says that pH is equal to minus the log, or minus the power of the hydrogen ion concentration. If you're told the power is 1 times 10 to the minus 2, then the pH is going to be the negative of negative 2, which is 2. The pH is 2. And so, of course, that's going to be an acidic solution since 2 is less than 7, right? 2 is less than 7. Let's try this one. The hydrogen ion concentration this time is 1 times 10 to the minus 6. So what's the pH? Negative 6, 6. The pH is 6. We're still less than 7, so the solution again is going to be acidic. Now, what if the hydrogen ion concentration is 1 times 10 to the minus 7? Now the pH is neutral. Now the pH is 7, because negative and negative 7 is 7, so the solution would be neutral this time. And finally, if the hydrogen ion concentration is 1 times 10 to the minus 12, pH is 12. The negative of the power is the pH. So negative and negative 12, pH is 12. Now this time, though, we're talking about a basic solution because of the fact that, well, 12 is above 7. So we're talking about a basic solution now. So again, as long as the base is 10, you don't need a calculator. You don't need a calculator to do those types of problems. All right, just do them in your head. Well, what if the base is something other than 10? What if it's, for example, we have a hydrogen ion concentration of 0.020. So it's not 1 times 10 to the negative something, but it's 0.020. Well, for this, you're going to need a calculator. So let's do this. We're going to write the equation. pH is equal to minus the log of the hydrogen ion concentration. And the hydrogen ion concentration this time is 0.020, just like that. So let's put that in the calculator. We say negative, and by the way, use the negative sign at the very bottom, the one with the parentheses around it. log minus the log, it opens the parentheses for you, 0.020, close the parentheses, and hit the enter button, or the equal button. I get 1.69897. I'm just going to round it to 1.7. We'll talk about rounding a pH later. All right, so the pH is 1.7. Now, what if the hydrogen ion concentration is 0.00063? So I'm going to say pH is equal to minus the logarithm of 0.000, whoops, one more zero, 63, just like that. So I'll plug that in the calculator, minus the log, minus the log of 0.00063, close the parentheses, and here's what I get this time, 3.200. There's numbers after the 2, but I'm just going to round it off to 3.2, okay? So that's it. That's all you got to do. If you want to determine the hydrogen ion, or the pH, if you know the hydrogen ion concentration, and even if it's not 1 times 10 to the negative something, it's just a matter of plugging in the calculator and you've got it, okay? All right, what if we want to determine the hydrogen ion concentration and you know the pH? Just go the other way. It's just as easy since pH is equal to minus the log of the hydrogen ion concentration. So let's just say the pH is 2. So what is the hydrogen ion concentration? 1 times 10 to the minus 2. What if the pH is 7? The hydrogen ion concentration becomes 1 times 10 to the minus 7. What if the pH is 12? Well, the hydrogen ion concentration is 1 times 10 to the minus 12. We can go on all day doing this. It's easy. All right, let's move on to a definition. What do we mean by amphoteric? Well, actually, we've encountered an amphoteric molecule before. When we were doing chemical reactions, we found that water we were not doing chemical reactions. It was earlier in this series. We were doing acids and bases, and we determined that water could either act as an acid or a base. And that's exactly what amphoteric means. It sometimes acts as an acid, sometimes as a base. Now, you might say, well, wait a minute, I thought water was neutral. Well, it is neutral, but it can accept protons or it can donate protons, making it an amphoteric molecule. So that's what amphoteric means, okay? Now, the products of an acid and a base, if you put an acid and a base together, you get a salt and water. Let's illustrate that. If I put it, be specific. Let's say I have this acid. I have hydrochloric acid, HCl, and I'm going to mix it with a base. Sodium hydroxide is a base, so NaOH, just like that. The salt that you're going to get is going to be the combination of the sodium and the chlorine. You're going to get sodium chloride. So you're going to get NaCl, and you're going to get water. So in other words, from this acid and this base, you get salt water, which is neutral, right? It's neither acidic nor is it basic. So case in point, right? When you put an acid and a base together, you get a salt and water. We won't forget that. Okay, let's move on. We want to calculate the pH for the following solutions and identify them as acid or base. So I'm giving you hydrogen ion concentrations. I'm not going to say it's 1 times 10 to the minus negative something because that's going to make it too easy. I want you to plug these into the calculator. So let's start with a hydrogen ion concentration of 3.8 times 10 to the minus 14. Let's do that. So we can write this out actually. We're going to say pH is equal to minus the logarithm of 3.8 times 10 to the negative 14. Times 10 to the negative 14, just like that. Okay? So what do we get? Well, let's plug that in. We get minus the log, minus the log of 3.8 second EE negative 14, just like that. And here's what I get. I get 13.4. 13.4. And, of course, 13.4 is above 7, so this is basic, right? Basic. Now, let me give you a little tip. If you don't have a value of like 1.0 times 10 to the minus 14, but it's something like 3.8 times 10 to the minus 14, the 3.8 is not going to shift the pH that far away from 14. So you're looking for a number close to 14. If I had gotten 2.8 or something ridiculous like that, that's a problem, right? But 13.4 is pretty close to 14, so I'm comfortable with that answer. In the same way, in this second one, let me erase this so I'll give myself a little bit more room. In this second one, this time I've got a pH or hydrogen ion concentration of 2.6 times 10 to the minus 6. I'm expecting something pretty close to 6, okay? Because the 2.6 is not going to throw me that far away from the 6. So let's see. We get pH, so pH is equal to minus the logarithm of 2.6 times 10 to the minus 6. So that's equal to what? Well, let's plug that in the calculator. We get minus log minus the log of 2.6 second EE negative 6. When I plug that in, here's what I get. 5.58. Let's make it 5.6. I'm just going to round it off to 5.6. So 5.6 is the pH, and that, of course, is acidic, just like that. Okay? It's an acid. Now, as I told you, I was expecting a number close to 6. Well, I got it. It's 5.6. That's close enough. All right? The next two I'm going to let you do on your own. It's the same exact way, so there's no point in me taking time to do those. But the point is, I would expect the third one, when you do it, is going to be close to 10, because the 5.6 is not going to move it that far away from 10. And then the last one, just plug it in. That's 8.5 times 10 to the negative 4, right? Or 8.75 times 10 to the minus 4. You can just plug it in into your calculator as 0.000875, I'm sorry. And that should get you the right answer, okay? So you answer those two. Now you should be able to do those on your own. All right, now that we can calculate pH from the hydrogen ion concentration, let's learn a few more rules about acids and bases. So here's the first rule. Rule number 1. The sum of the pH and the pOH is 14. So if you know the pH, then you know something called the pOH. You may say, what's pOH? I've heard of pH, but what is pOH? Well, pOH is another way of indicating acidity or basicity, okay? So you have a pH, you have a pOH. If the pH is one number, like say 7, then the pOH is 7. But if the pH is 3, the pOH is going to be 11 since pH plus pOH is equal to 14. So 3 plus 11 is equal to 14, okay? So that's the first rule that we're going to remember. pH plus pOH is equal to 14. Rule number 2. And this really comes from rule number 1, mathematically. The product of the hydrogen ion concentration and the hydroxide ion concentration is a constant called Kw. And that constant is this. It's 1 times 10 to the negative 14. That's the number. 1 times 10 to the minus 14 is the constant. So if you multiply the hydrogen ion concentration times the hydroxide ion concentration, you're always going to get the same thing. 1 times 10 to the negative 14. Now that gives me an interesting opportunity here, because now if I know the hydrogen ion concentration, I can just say 1 times 10 to the minus 14 divided by the hydrogen ion concentration is equal to the hydroxide ion concentration. So if I know one, I know the other. So if the hydrogen ion concentration then is 1 times 10 to the minus 3, the hydroxide ion concentration is 1 times 10 to the minus 11. All right? And by the way, remember, when you multiply numbers with exponents, the powers are simply added. That's how I was able to get that so easily in my head. Minus 3 plus a minus 11 is a negative 14. All right? So that's that. All right, I want to talk now about something called titrations. What do we mean by a titration? Well, a titration is a procedure. Okay, it's a procedure in which the unknown molarity of an acid or a base is determined by neutralizing it with a base or an acid, the opposite one, for which the molarity is known. So this is a titration apparatus here, okay? And so what we've got down here is we've got a flask, and it has an acid. It could be a base, but it usually is an acid, and it's got an indicator in it. We'll talk about what an indicator is in a moment, but for right now, we'll just say that it's a chemical that indicates whether it's acidic or basic, right? And up here we have an instrument called a burette, all right? A burette is a very precise measurement device that holds fluid, but it measures the volume that you place that you release into the flask, right? Through a device that kind of turns, and it's called a stopcock. And that device allows us to very precisely, even drop by drop, deliver a specific amount of base or acid, again, depending on what the titration involves, into the acid, all right? Or the base, depending again on what the titration is. But remember, there's an indicator there, and we're going to talk about that indicator. So an indicator, which is, by the way, usually phenolphthalein, is placed into the flask to give a visual signal as to when the neutralization has taken place. So note, phenolphthalein is clear at pHs of less than 7, but becomes pink as the pH reaches levels above 7. In other words, it becomes more basic. So when phenolphthalein, the indicator, turns pink, you're dealing with a more basic environment in the flask. So this equation is going to be important for titrations, and here it is. At the titration point, what we mean by titration, when there's neutralization, the molarity of the acid is equal to times the volume of the acid is equal to the molarity of the base times its volume. So at titration, again, that means neutralization. That means we've neutralized acid and base. The molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base. Folks, we're going to pick up titrations again in the next one. I'll see you on the next one. Thanks. Bye.